It's not like, it could be 2 hours away.
I love lemon. What you do? Lemon? It's just like
all right, usually we don't kick things off till 7, but since we've got seats and everybody's sitting, I figure we'll get started now. Welcome all. How many of this is your first LVTech meetup? Wow, so many. Why? It took you so long. We do this every month. Usually it's either a technical presentation like tonight. We're talking explore some technical topics. Sometimes we got a couple demos. Usually we're up on the mountaintop in Bethlehem, Ben Franklin Tech Ventures, but it's good to move around a little bit every once in a while. But if you obviously if you're here, you probably joined us on Meetup, so I'd love for you to kind of keep in touch with us there. And I think next month's Meetup will be interesting too. We're going to have that at the Northampton Community College's the South Side campus there in Bethlehem at their newly renovated, well I shouldn't say renovated, it's a completely new space. They moved the Fab Lab down to the first floor. So if you've never been to a Fab Lab, it should be interesting. It's got a bunch of modern fabrication technology there, so you immediately think of things like 3D printers, and off the top of my head I think they have like 3 or 4 of those, all different technologies. They have some of the depositor, whatever you call it, additive, I don't know what it's called, but the thing that squirts out like hot glue. They've got a bunch of those. They have the SLA, which is the stuff where you sinter resin with lasers or something as it kind of comes out of this vat of goo. It's pretty cool, but high resolution prints. They got all that stuff. They also have some laser cutters, which are really interesting. Full wood shop. I think they have a couple machine, like a Tormac and some other metal mills and things like that. So it's a really interesting place. I've not been there since they've opened the new wing, so it should be interesting to see. So if that's of interest to you, love to see it there next month. Just a little heads up on that. I think we're going to have to push it another week just because of my travel schedule. So it'll probably be a week later than Meetup says it is, but I should have confirmation on that pretty soon. Other than that, I think I just want to thank Seed Development for having us here tonight, and Matt's going to come and tell you a little bit about Seed.
Hey guys, welcome. Thanks for coming, and we're happy to have all of you here. Give you a little bit of background about Seed Development, real quick, so we can get to the stuff that y'all came for. I'm from Pennsylvania originally, up north in just outside of the great town of Hazleton. My business partner in the back is Noah. He's from Long Island. We were both out in New York for a couple years. We decided to start our own consulting company. And after about a year or so of business, we came back out to the Lehigh Valley. A lot of the work that we do, we're big Google partners, so we do a lot of stuff on Google Cloud. We do a lot of app dev. We do work with a lot of companies still in New York, mostly in New York. And I think one of the things that was our initiative of kind of the second half of this year was to start doing business with more companies in Pennsylvania in the Lehigh Valley. And actually be community members. Part of that is obviously having you guys here and hosted. Would the Seed guys raise your hand real quick? And girls? Girl? So that's the Seed guys. So if you guys want to know about any projects that we do or have done for Price Waterhouse or Citibank or Formula E Racing or crazy other stuff that we do, feel free to ask these guys afterwards, and they'll be more than happy to answer. And that's about it. Again, and those in the green fleece, you can't miss them. Normally we do this awesome like Penn and Teller thing where I'm the big loud one and he just stands beside and nods and does all the real magic. But we're around if anybody needs anything. Bathrooms down here, there's 2 of them, men's and women's, but for intents and purposes of tonight, feel free to use both and lock the door. They're both reasonably clean. And other than that, I will happily turn it back over to Tim.
All right, I'm not going to do much more than introduce Chris, who's our presenter for tonight. Chris is the organizer of Lehigh Valley Crypto Tech and partner of RigShare, which is a crypto mining company. So he's going to tell us about the blockchain. Turn it over to him.
All right, first task here is to figure out this. All right, thanks everybody for coming out here tonight. Also thank you to LVTech and Seed Development for hosting this. I've been looking to get in front of a little bit more technical crowd for a while with this instead of just talking about trading and markets and everything. So we're going to give a technical introduction to the technology behind the cryptocurrency phenomenon here, and hopefully it's not going to be too technical. Hopefully it will be technical enough. Hopefully I've struck a good balance here. So it's going to be some parts I'm going to speed over, some parts I'll slow down when we get into the weeds a little bit, and hopefully all around you'll be able to take something out of this. If I did my job today, you'll probably walk out of here with more questions than you had coming in. So let's get started here. So what you've probably heard is about volatility and markets going up and down all the time. Here, this is just the past 1 month's chart of Bitcoin. It was as high as over 8,000, as low as under 6,400. You might have heard about a lot of breaches and hacks and things like that. If anybody here was, I don't want to, open up any wounds here. If anybody here was affected by nice hash, but over 4,700 Bitcoin was stolen, which at the time was worth $62 million. And then, of course, you also hear all the people, especially if you go on social media like Twitter and things like that. It's very vaguely the future, and you should buy. They're going to tell you that right there, that's as low as it's going to go. I don't know if they're right. I hope they're right, but so what you probably haven't heard is who's really using this stuff right now. How does it actually work? When is it a good idea to use? And you probably honestly haven't heard much of this in total speculation. And also, to be honest, I don't think we're going to be able to answer all those questions firmly here today, because these are things that are very much still being worked out. So in the news, I just pulled out some articles from CoinDesk over the past week, which I thought were interesting. To cover the whole gamut. You have government getting involved with trying to use blockchain to secure digital evidence. You have patents are becoming a big thing. The intellectual property wars are very much starting with this stuff. So Coinbase winning a patent here to secure Bitcoin payment systems. Up here I have UPS looking to use blockchain to try to track global shipping data, which goes into one of the larger use cases right now of supply chain management that a lot of people are really optimistic about. You also see a lot about things being funded lavishly here. An Overstock spinoff was able to raise over $100 million for some mysterious blockchain-related project they're doing. And I'm sure you've heard about a lot of that kind of stuff elsewhere. And also then government stepping in with regulations. How are governments going to allow people to use this? How are they going to understand the technology? And are they going to let it grow or not? And I think that answer is going to vary government to government. So where did the hype go? I think in December, I think we can agree that if you've ever heard the hype cycle, that we were right around there in December, and those people who are calling the bottom of the market are now trying to say that you're all the way down here at the bottom of the trough of disillusionment, and that we're now going to head gloriously up the slope of enlightenment. Again, maybe we'll get there, but this is something that a lot of people following new technology trends look at, and very much so it does seem like we are, at least in this part of, or in this cycle, we're past this for sure. So a bird's eye view of what we're going to be looking at today is kind of like this. This is what I see a lot of people tend to have in their minds about what cryptocurrency is, what blockchain is in general. They know that there's this vague blockchain concept, that there's something going on all over the world. They know that miners are doing something with the blockchain, and you have users who are usually connecting to these services like Coinbase, mining pools, or exchanges to either buy, acquire, or trade these these cryptocurrencies. So we're not going to be too interested in these services here, because these are really just centralized services which are built around blockchain and don't really have much themselves to do with blockchain. So when you see something like NiceHash being hacked, it's not so much of a flaw in blockchain, it's more has to do with these services that had some issues. So just to introduce the distributed ledger, a lot of people by now also know that the blockchain has something to do with storing a distributed ledger. And you've probably heard that basically the blockchain is storing all transactions which have ever occurred in the example that we're going to look at a lot, Bitcoin. We will move past Bitcoin a little bit, but for the most part, we're going to be talking about Bitcoin. So all the transactions since the beginning of the blockchain are stored in this ledger permanently and irreversibly. So just in this little very basic example, I have the beginning of time here. Alice creates 25 Bitcoin, sends some to Bob, and Bob sends some to Charlie, and all of this. And then once you get down to here, where Oscar tries to send Bob 100 Bitcoin, one of the guarantees that we expect from these networks is that we see Oscar never had any Bitcoin to send, and so this sort of fraud will be easily picked up and not reported into the blockchain. So that's just the introduction to the concept of the distributed ledger, which is going to come up a few times. So now I want to just go through quickly a couple of transactions that you're already familiar with, and then we'll go into what transactions look like in Bitcoin, and we'll get into a little bit more detail then. So I'm just going to speed through here. What's going to happen if meet Alice and Bob? I'm sure many of you have already met Alice and Bob in the past. But let's say Alice wants to give Bob $5 and she thinks she has $15. So they check that she has $15. She's got to log into her bank and she doesn't physically have it. And then she tells her bank to go and send that $5 to Bob. And then the bank, maybe Bob has another bank, and so they have to communicate. There's going to be a fee involved. So in this quick example, the bank's taking a $2 fee, and Alice is left with $8, and Bob now believes he has $5, which better be true if he's trying to write any checks. But the concerns here are how much of the fee is going to be, how complicated is this transaction, can the banks be trusted? The birth of Bitcoin really came out of the 2008 financial crisis, so there is very much a distrust of banks and third parties in general. Can we disintermediate the middlemen in many industries is one of the big questions that we face with blockchain. Will I be able to get my money out in the event of a run on the bank or something like that? Will you actually be able to get it? And what if I don't have a bank account, or maybe more importantly, I'm unable to get a bank account? One of the big applications that people have thought about since the beginning of blockchain is banking the unbankable, so to speak. There's a lot of people in the world who don't have access to financial services, so one of the beliefs is that things like blockchain might enable these people to connect to financial services that weren't available to them before. So now let me talk quick about a cash transaction, because this is closer to what we're trying to do, and also somebody who doesn't have a bank account, this might be what they do. So Alice has in her wallet here a $10 bill and a $5 bill. She wants to give Bob $5. You can guess what happens here. She gives Bob $5, not much of an issue. The concerns here, though, are how are they physically going to exchange? Can they meet in person? Does it have to be mail? Things like that. Can I get to them? Do they trust the value of the fiat? You're still connected to the currency, which, by the way, is a criticism of cryptocurrency, hasn't held its value much, against fiat especially. But next, does Bob trust that it isn't counterfeit, which I think is an interesting one when you consider cryptocurrency, because cryptocurrency and blockchain sort of solves the counterfeit issue, where with fiat currencies today, you have this cat and mouse game between the counterfeiters and the people trying to print the currency. With cryptocurrency, that's sort of just built into the system, which is a case for what a lot of people would consider crypto fiat. If governments would try to issue this stuff, that would be a tremendous incentive to governments to pick this up. And finally, what if Alice wants to give Bob $6, just as a little technical note? Well, he didn't have any money to begin with. If she hands him a $10 bill, he can't exactly give her any change. So now I'll slow down a little bit to go into what a transaction looks like in Bitcoin. And I just want to point out a couple of details, because a lot of you are probably already familiar with much of this. But I'm now going to say that Alice has 15 Bitcoin and she wants to give Bob 6 Bitcoin. The first thing that I just want to call attention to here is that in Bitcoin, and not all cryptocurrency networks, but in Bitcoin, there is this concept of what really is analogously bills. Your wallet, you'll see that you have 15 Bitcoin, But in the system itself, it's actually going to have these things that are called unspent transaction outputs. Not a phrase I'm going to use a lot here, but just in case you hear it, a UTXO, that's what this refers to. Your wallet that has 15 Bitcoin is actually made up of a 10 Bitcoin bill and a 5 Bitcoin bill. And I just want to work through this example to see how that's spent and how this sort of works out. So the first thing that Alice is going to do is she wants to tell the network that I want to send the 6 Bitcoin to Bob, and I'm willing to pay 6.001 Bitcoin for you to do this. That extra 0.001 Bitcoin is going to be the fee that ends up going to somebody in the network, and the 6 Bitcoin then is going to go to Bob. Now she also commits this UTXO of 10 Bitcoin to pay for this. So then she no longer has a 10 Bitcoin bill in her wallet. The blockchain network is going to split this into 3 parts. It's going to basically destroy that 10 Bitcoin bill, create then one 6 Bitcoin bill and give that to Bob. It's going to create a 0.001 Bitcoin bill and give it to somebody in the network. And then it's going to create the remainder, a 3.999 Bitcoin bill, and send that back to Alice as change. And so then now her wallet looks like this. It's sort of a strange concept in Bitcoin, but you might often hear that Bitcoin are arbitrary. You can make them up to, like, I think it's 8 decimal digits that you have. Like, you can create a Bitcoin arbitrarily, but once it's created, it's indivisible, and it has to be destroyed in the transaction like this. So just an interesting little quirk of Bitcoin. And so with that stated, that part, we can kind of forget about all the bills now. We just want to get into how do Alice and Bob actually create accounts on the Bitcoin network. And to get into this, I'm going to start talking about the abilities of a user. On a Bitcoin network, a user should expect that they can create anonymous identities, receive funds from anybody, send funds securely, and also trust the integrity of their transactions on the network to prevent from anybody, any third party, altering it, basically. So to start with this, I just want to really quickly say cryptography is very important. Very, very important. It's what separates cryptocurrencies and blockchain from any other digital money before it. From Wikipedia here, cryptocurrency is a practice and study of techniques for secure communication in the presence of third parties called adversaries. For blockchain users, this really means protection of your digital funds and assets from people who might want to take them from you. So the branch of cryptography that is most, I think, exclusively used in Bitcoin and blockchain networks is called public key cryptography. And this is a system where users are going to maintain pairs of keys, where one is private and one is public. So the private key is known only to you, and it can only ever be known to you, or else somebody else is going to have access to your funds. The public key is going to be derived from the private key mathematically, which can then be shared with anybody else for them to basically identify you on the network and send money to you. And most importantly, with the knowledge of your public key, people are not able to derive the private key. And then just to put it very simply, the private key allows you to spend funds, the public key allows you to receive funds. I'm going to get a little bit into the keys here though. So becoming your own bank, cryptographic keys. This is how Alice and Bob are actually going to establish their identities on the blockchain network. Typically, you'll see people opening an account on Coinbase, on an exchange, maybe one of these light wallets, a concept we won't get into here, but if you've heard of Electrum or Jax, or maybe something that you have on your wallet or on your phone as a wallet, maybe something like that, it helps you create it. Or maybe you'll run a Bitcoin Core full node, which we'll go more into detail on full nodes in this presentation. Or my preference is to flip a coin 256 times, which I don't want to say if I actually have done or not. I've been looking at this stuff too long. So private keys. A private key is a 256-bit number that only you will know, or else somebody else will be able to use your funds. It is the cornerstone of your right to digital property. So if most of you are probably familiar with what I mean by a 256-bit number, but it's just a sequence of 256 binary digits, 0 and 1. So this right here would be a valid private key on the Bitcoin network, and I don't have any money in there because obviously I'm not the only one who knows it. So randomness is very important when you're creating keys. Because even accidentally, if you're using for random number generation, somebody could actually accidentally generate the same private key as you. So you always see these warnings about needing a lot of randomness in the private keys, and it is very important. Because I guess what I'll lead into here is that I know a lot of people, when they look at this, they think like this is probably pretty easy to guess, but it's not easy to guess. Because there's 2 to the 256 combinations of possible private keys, which works out to about 10 to the 77th, which is comparable, it's less, but comparable to the number of atoms in the visible universe. And more practically speaking, if you took all the computers on Earth right now and had them just trying to guess somebody's private key from the beginning of the universe, they would still have a very small, I think less than 0.1% chance of having guessed your private key. But if you don't have the proper randomness in your signature, somebody who just accidentally uses the same method could create the same private key. So terribly difficult to guess, terribly easy to screw up randomness. Now public keys are derived irreversibly from the private keys, which are what you're going to be sharing with people. And I'll just run through this quick. I'm not trying to get too into the math, but I do think it's interesting to note that the equation for creating a public key from a private key is just this up here. It's the capital K equals little k, which is the private key, times this generator called G. That gets you your public key. Except this math is done in an algebra called elliptic curve cryptography. And as it turns out, in this algebra, if you try to solve this for the little k, the private k, to go backwards, you just can't do it. It's something known as a discrete logarithm problem. So if you're really interested in that stuff, these are some of the phrases that you could look up. But in general, you don't have to worry too much about this stuff if you're not interested. But it's certainly there. So with the public key, once you generate your public key, it's actually going to look something like this, which doesn't look like much of a number. In fact, it looks like 2 numbers. So we don't really like to use this in the blockchain networks, and in Bitcoin and pretty much every blockchain that you might see, the addresses are going to look something more like this. Maybe they'll have a 0x in front of it, but essentially they're derived from these sorts of public keys, just to make them a little bit more readable, and also add some bits of security that we won't get into, checksums, things like that. So just to summarize that, what Alice and Bob have done so far, without needing to know any of that, is they've gone to their wallets, whatever wallets they're using, and they've created this 256-bit private key and generated a public address from that. And just to simplify this, for the rest of the diagrams I'll be using here, we'll just use a little KA for Alice's key here, her public address here, and similar for Bob. And anything to the left here, which is only ever going to be her private key, is something only known to her, and anything to the right of this little line here are things only known to Bob. Everything else, we don't care. Anybody in the world can know about it. So, digital signatures. How does Alice send a transaction without revealing her private key? So this is very important because if you have a private key and a public key, and the private key is how you spend funds, well, you could just spend your funds by giving somebody your private key. But obviously that would defeat the purpose of the system. So there's this clever mathematical system called digital signatures, which I will not get very deep into, but just to understand the features of it. In order for us to use digital signatures in transactions and be able to believe them, we need these 3 properties. We need authorization, meaning we need to know Alice actually sent the transaction. We need non-repudiation, meaning Alice can't be able to deny that she signed this transaction. And we need integrity, which means the transaction can't be changed once Alice authorizes it and submits it to the network. So what is a digital signature? I'll get lazy again here and just put the Wikipedia definition. It's a mathematical scheme for demonstrating the authenticity of a digital message or documents. And for blockchain, this really just means that we can verify transactions signed by a user's private key without knowing it and knowing it hasn't been modified. Essentially just those three properties we're able to satisfy with digital signatures. And if you want to look into this yourself, you want to look into ECDSA, which is the algorithm used for digital signatures, called elliptic curve digital signature algorithm. Now, I will walk through a little bit of an example, though, of how you will use a digital signature in a blockchain system without needing to know too much about actually how they work. So the first thing that's going to happen is Alice is going to create a transaction. And she's going to basically do this by, you don't even need the key yet. She'll just say, I have this money I'm willing to spend, and I want it to go to this address over here. Just constructing a transaction. How much I'm sending to who. And that's basically that. So then she needs to sign the transaction. So this is creating the digital signature. She'll take the transaction she's created and combine it with her private key to create this digital signature, which can be out in the public, but doesn't reveal her private key. Then Alice submits this transaction along with the signature to the blockchain network so that it can be verified, and then the funds moved over to Bob. And then once she does this, anybody in the world can then verify that given the signature and the transaction and her public address, they can use the address and the transaction against the signature to make sure that Alice actually sent or actually signed it. And the important thing to note here as far as the integrity is that once Alice signs this with the transaction, any attempt to change the transaction would actually require a different signature. And so it's very easy to spot when somebody tries to manipulate this. So that is that's digital signatures. That sums up the abilities of a user to create the anonymous identities with private keys, and you receive them at your address, and you can send funds trusting that they'll maintain their integrity because of digital signatures. So I know I'm speeding through that, but there's a lot of material. So, so now let's go into what happens after you send this transaction to the network. You submit it to the blockchain network, and as I mentioned before, we're mainly looking at the Bitcoin network. Now, the Bitcoin network is going to be made up of a bunch of computers running software that implements what you'll usually hear referred to as the Bitcoin protocol. So the Bitcoin protocols, and any protocol, whatever blockchain network you're looking at, is just a set of rules that all of the computers on the network agree to adhere to in order to establish the state of the distributed ledger. But the first thing that I'll say about the network is that it's peer-to-peer, meaning all of the nodes are connecting to each other directly, however they can, if they can reach them, instead of needing to rely on a centralized authority in order to connect to the network. But that's not quite the concept you usually hear, which is decentralized, because in this diagram, this could be a database server, this could be an IT system, this could just be a very generic mesh diagram of a business system. But what makes it decentralized is that each of these nodes is actually capable of performing the same functions and maintaining the blockchain in the same capacity as every other node. So we're also decentralized in these networks. And these are the four major functions that a node is able to do. A node doesn't have to do all of these functions, but if it does all these functions, it is contributing the most to the security of the network, which we'll show a little bit here. But just to go through these quick, you have the networking component, which is just how it establishes the peer-to-peer connections and routes data through the network. You have the wallet, which is going to be responsible for managing the keys, your private keys, your addresses, creating your digital signatures, things like that. You'll have the blockchain, which is going to be the entire distributed ledger, or I should say a copy of the entire distributed ledger on this computer. And then you also have mining, which will be the creation of new blocks on the network. So the goal is going to be to reach consensus on the state of the network so that all of the nodes share a common distributed ledger of all the transactions, obviously. I guess I've said that a few times. But, and we also need, not only do we need to agree on the state of all the transactions that have happened, we also need to agree on how to update this ledger of new transactions. So why is consensus difficult to achieve, though? This was a problem up until Bitcoin was created. And you'll often hear that Bitcoin solved something called the Byzantine generals problem, which is just a motivating example for why this is difficult to achieve in distributed networks. I'm not going to go into that here, but it's another thing that you might be curious about. It is a kind of a cute little analogy. But the gist of it is that nodes are privately owned and mutually distrustful. I own my node, you own your node, I don't know what you're doing with your node, I kind of don't want to know. But and you don't know what I'm doing with my node either. And nodes are also just physically separated and communicate digitally. It just creates a logistic issue. You know, how are we able to do this when the only link that we have is, you know, our LAN, or, you know, our Ethernet port, or Wi-Fi, or whatever it may be. And then nodes can be malicious and attempt to insert bad transactions. You know, again, I don't know what you're doing with your node. You could be doing anything malicious. I need to not have to worry about that. I basically need the network to overcome whatever malicious intent we might have. So this is what makes consensus difficult, and we end up solving this with blockchain and proof of work. So now let's get into blockchain a little bit. Blockchain is an implementation of a distributed ledger. You take the same example I gave before, and essentially this is going to be broken up into these individual blocks over time. The beginning of the ledger is going to be put into the first block. We'll just say maybe in the first 10 minutes of the network, these are all the transactions that occurred. Then we need a way to include transactions that happen after this block, and so we'll create a new block with all the transactions that have happened after that, linking this block to the previous one. So this little arrow here is pretty important. So we need a way for the current block that, you know, is the state of the network to also reference the old blocks. That's what that link is going to be. We're going to explore that a little bit. I'll also just note quick that block 0 is always called the Genesis block. You've probably heard that, but just traditionally, the beginning of any blockchain tends to start with what they like to call the Genesis block, and it just builds from there. And it builds up and up and up and up and up. This is the Bitcoin, where the Bitcoin network was at as of last night when I was rushing to get this presentation together. So so we were at block 538808, and this would go all the way down to the Genesis block, block number 0 in Bitcoin. And you can see that you had 2,906 transactions. In the block before, you had 2,242 transactions. You can kind of get a sense of one of the issues here, actually, with Bitcoin. And that's, these blocks occur once every 10 minutes by design. A new block is going to be created. And we're only getting a few thousand transactions in each worldwide. And this works out to something, I didn't calculate for these exactly, but I know the general average is something between 5 and 7 transactions per second that the Bitcoin network is actually able to settle. And when you're looking at the big, you know, the pot of gold at the end of the rainbow kind of applications that people dream about, like competing with Visa and MasterCard networks, those things I believe are doing something like tens of thousands of transactions per second. I don't know that exactly, but I know it's a lot more than what this is doing. But I digress. I want to get into now what is a block. Let's just keep breaking this diagram down a little bit. A block is going to contain all the information that we need to store transactions and cryptographically link it into the blockchain. And we're going to, well, and by the way, the more interesting part of that is definitely the second part. And we can identify a block by its height, which is just the next number in the chain, but then getting into that second point a little bit, we can also describe a block by its cryptographic hash. So what is a block hash? The block hash is what we like to call a cryptographic summary of the entire block. We take this whole block and all the transactions in it and all the other information, including its link to the previous block, and we put this into something called a hash function, which in Bitcoin is the SHA-256 algorithm, which is going to give us a 256-bit sequence that gives us our block hash, essentially. And you might notice there's a lot of zeros in front of this. That's not by accident. And we'll get into that a little bit when we get into the creation of new blocks for mining. But the important thing to realize for right now is that if I try to change any part of this block, any of the actual contents inside of it, the block hash, or I should say even slightly, as I say here, the block hash is going to completely change. So it'll be an entirely different block hash. So that's a block hash, but why are the block hashes important? Just to give a sense of this, as I described, the blocks are linked to each other using the block hash of the previous block. That's actually what this link is. It's saying, give me the hash of this block, and I'm going to store that in my block. So we're linking the hash of that previous block into the next block. Like I said, if any piece of information's changed, we're going to have a huge change in the hash. And that's going to invalidate the block hash, which was used to link the block to the next one. And this process is going to go up and up and up. So if I try to change a transaction down here, changing the hash of this block, that's going to change the hash in this link that's stored in this block, changing this hash, changing this hash, changing this hash. It's very easy to spot when somebody tries to change something. So the other thing to note, and we'll get into this a little bit more towards the end here, but it's going to become progressively more difficult to change transactions or blocks that are built on top of it. If I have a transaction back here that I'm trying to falsify, I will essentially have to redo all the work of all the blocks built on top of it to convince the system that I'm basically trying to create a different blockchain. I'm trying to convince the system that my blockchain is the correct one, to ignore this history, which has been built by all the other nodes on the network, and to use mine. So the further back in time we go, the more work I'm going to have to do as an attacker in order to falsify all the blocks afterwards as well. So now I want to talk about reaching consensus and the abilities of a node. These are four very important abilities that enable fundamentally how you solve the Byzantine generals problem, how you can achieve consensus in these distributed networks. And so just to list them off here, we're able to independently verify transactions, create new blocks, verify new blocks, and assemble and select the active blockchain. And I'll tell you right away, by far and away the most complicated one here will be creating new blocks. So with independently verifying transactions, I've already kind of looked at that a little bit when we talk about just checking the digital signatures. Anybody can validate that. You also just need to check some other basic accounting things like, does this person have the money that they say they're trying to spend? Are they trying to spend money they've already spent, or a double spend as it's known? Just things like that. So pretty straightforward with that. But the process of creating new blocks on the blockchain, also known as mining, which is a little bit more my wheelhouse, is a competitive process that all the nodes on the network are attempting to create the next new block. And only one node at a time is going to be able to create a block. And when it is able to prove that it has created a valid block, it's able to collect the mining rewards, which includes the block reward, which in Bitcoin I think is something like 12.5 Bitcoin right now, and also all of the transactions that of all the transactions we included in the block, we're able to collect all the fees on those. And so I think that covers everything on this slide. I guess I'll just mention quick that the creation of new blocks is computationally difficult by design because of something that we'll get into called proof of work. So let's see what I have here. How do we construct a new block? The first thing we have to do is create the candidate block. And that candidate block is going to be formed out of transactions that haven't yet been included into the blockchain. And the way that we try to organize them, even though it's not an exact process, we try to maximize the amount of fees that we're going to be able to collect from the transactions that we include. And the interesting thing about fees, which is probably not something I thought I'd ever say, but the interesting thing about fees in blockchain networks is that they're actually based on the amount of space that your transaction takes up physically in the block. This is why you can send like 10,000 Bitcoin or 0.01 Bitcoin and it's the same fee. It's actually the amount of space in kilobytes, bytes, whatever that your transaction takes up. So we try to organize the blocks in such a way that we're going to maximize that. And of course, we're not doing that manually. This is all done automatically through the software. So once we create this candidate block, we need to go and solve what's called a cryptographic puzzle to prove that we've done enough work to add it to the blockchain. Basically to convince other nodes, not just us. We could do it ourselves as much as we want, and we'd be happy with it. But to prove to other nodes on the network that we're doing sufficient work to actually add it to the blockchain, that takes a little bit of wizardry. So to get into mining, just a little bit here, to get the concept of really how it works internally, we have to look at what's inside of a block. So just take this block and let's just make it very generic. You'll see we have these fields. We don't care about them all. The only one we really care about is the block header. And the block header then has fields itself. You just go deeper and deeper into it. We also don't care about all of these, but we know we have a block with all the transactions, including a block header. A block header's got this stuff, and we're going to take a look at some of these things. Now, the first two we can knock out of the way pretty quickly. The previous block hash is what we already were looking at in terms of that arrow in the diagram. That's just the link to the previous block, and it's its block header hash. When we're creating these hashes, we're actually hashing the block header. So this is really the previous block header hash. And then the Merkle root, which is a concept I'd love to go more into, but I think is a little beyond the scope here, is a cryptographic summary of all the transactions in the block. Because you might have noticed when we looked into the block header, I discarded the rest of that information. Some of that information was all of the transactions. But we still want a way for all the transactions to be reflected into what we hash. We just don't want to have to go through the computational effort of taking thousands of transactions whenever we need to do this. So we create this cryptographic summary of all the transactions in the block and put it into something called the Merkle root. The Merkle root is tied to the concept of a Merkle tree, which is an interesting data structure in itself, but we won't be going into that. So I guess the point to take away here is that we're able to include the information from all the transactions into the block header through the Merkle root in such a way that if anybody tries to falsify a transaction in the block, it's actually going to show up here and then invalidate our block header hash, and hence the rest and the rest. So the remaining two is where we can talk about proof of work. We have the difficulty target and the nonce inside of our block header. And in order for the cryptographic link in the blockchain to mean anything, it needs to be provably difficult to create the new blocks. And so we create this condition that the block is only going to be valid if, just to lay it out there, this is a rough equation actually, it's not quite exactly like this, but it's close. But if the SHA-256 hash of the block header is less than the difficulty target. And this is why when we looked at the block header hash before, with all the zeros in front of it, this is why it has so many zeros in front of it. It actually needs to be less than a certain number, and so we're actually trying to find a relatively small number, just numerically, to hash this block header into. So the difficulty target is going to set the parameter, right? We need this is a little bit of a summary of what I was saying already, but it's going to be up to the miner to find the correct nonce. So the nonce is the really interesting part to a miner. If I'm trying to create this block, the only thing I need to do is find a value of a nonce that I can then put into the block header, hash with all the information, and get a value that's less than the difficulty target. If I don't get a number that's less than that, I just try another nonce value. And it's just guesswork. You can just count from your fingers, 0, 1, 2, 3, 4. There's no optimal strategy in a guessing game. And so this is what makes creating these blocks so difficult. We just have to participate along with all the other nodes in the network in this guessing game. And it takes a lot of energy It takes a lot of power, especially when you have the number of computers on the network like you do with Bitcoin. So basically it's impossible to solve this equation analytically, so we have to guess, is what I was saying here. So once we do find that valid nonce value, all we do is we stuff it into the block and send it away, send it to all the other nodes and ask them, hey, check this out, I found this solution, isn't this cool? And if they do think it's cool and they accept it into the blockchain, then we're going to be awarded with the block reward and the transaction fees. So this is really how we do mining. It's a really strange, it's a novel concept if you really think about it, but I'm fascinated by mining, so I'd love to talk about it more and more. You can get in touch with me about that though. Just a couple final notes on this. A difficulty target is periodically changed to reflect the amount of computational power that's on the network. That's why it's not hard-coded. That's why it's actually part of the block itself. And in Bitcoin, this changes about once every 2 weeks. So there are some implications of that I'm not going to get into here. But yeah, every 2 weeks about, this number is going to change. And since the first guess or the last possible guess are both as good, like I said, no optimal strategy in a guessing game, we get a lot of variability from 10 minutes. When I say the system's designed to create an expected block time of 10 minutes, well, I mean, there's a lot of variation from that expected time. Over the course of Bitcoin's 8 or 9 years here, it's been very close to 10-minute block times on average. But you're still sitting there at your computer sometimes waiting an hour and a half for 2 confirmations to get your money into an exchange or something. So it can be a very frustrating experience. Now, the last thing I'll note here is that there are many possible nonce values that can produce an answer here. It's not just one. The inequality is just to get something that will produce something less than the difficulty target. Well, there's a hell of a lot of answers that you could come up with. It's just that to find any one of them should take us an average of 10 minutes. So that's how we create blocks, and when we create it, ship it out to somebody else with our nonce, and they, along with us, can verify these blocks independently. I just take it, I look into the block header, I hash this information, and if this equation is satisfied, boom, I've got the block that I believe whoever mined this block was actually able to do so. And this is where we have the concept of it's incredibly difficult to create these blocks, but incredibly easy to verify them. And we need that property. Because if it was difficult to verify these blocks that are being created, then we'd be spending as much time verifying as we are creating, and the system just doesn't work. This is very crucial to why we were able to establish consensus using this system on these networks. The last thing that we can do in order to reach consensus on these networks with our node is to independently assemble and select the chain. I'll go through this kind of quickly. This is a far more interesting topic than we have time for, but since each block implies a proof of work, then the entire chain implies a cumulative proof of work. And we basically will select the blockchain, the active blockchain, based on whatever blockchain that we're looking at has the most total proof of work. And where this comes into play can be one in the case of fraud, like if I say, to go back to the example where somebody tries to falsify a transaction back here, this is why they have to replicate all of this extra work on top of it. Because if they don't replicate all of the additional work, then we see that their chain only has this much work with this bad transaction, while meanwhile other people on an honest chain with a correct block down here have all this additional proof of work. So essentially, if I'm an attacker, in order to have any chance of actually convincing the blockchain that my blockchain with the falsified transaction is the correct one that should be selected, I need to do more work than everybody else, which is where the concept, if you've heard of the 51% attack, comes from. If I have the majority of the mining power on the network, then I have basically a good probability of being able to convince the network that my chain is the correct one. And that just comes from the very concept of consensus itself. The whole concept of consensus here is if most of the nodes on the network are able to agree on the state, then that is the state. If an attacker has more than all of the honest people, then he has to say what the state is. But luckily, there's a lot of good, honest nodes in a big network like Bitcoin that it's not so much of a concern. It can be a concern for smaller networks. You go to 40, 50, beyond in the coin market cap list, if you've ever seen this list. A lot of these networks are too small to really have the sufficient security to defend against attacks like this. So those are the four abilities of a node that allow us to reach consensus, whether it's just us mining on the network or it's thousands and thousands of nodes. All the nodes in this decentralized way are just doing the same thing over and over. Just by doing the same thing and agreeing on it, they're able to create a lot of redundancy into the system, which ends up being security when you're trying to maintain the state of something like a distributed ledger. So it's not perfect. As I mentioned, we have 51% attacks that can happen on smaller networks. We have the energy consumption from proof of work, which is a big environmental concern. You know, I, in my operation, have about 40 of these miners running, and it's hot and it's loud, and we almost need to bring a new line into the building just to expand the operation. It's a huge, huge energy cost. We also have slow block times, overly variable block times, and being unpredictable in their variability. We have the transaction processing limits. We have something called a block size limit. We have the size of a blockchain. I mean, the Bitcoin blockchain is something like 200 gigabytes. I don't know. It's probably around there at this point. And it's only going to grow and grow because we always need to maintain the entire history. These are serious issues. And there's a lot of ideas on how to move forward with it. But you can't look at blockchain and ignore all these things, especially if you're trying to look at tinkering with it or even using it in a business application. And also, they're anonymous but not private. Yeah, nobody knows who you are, but they can see everything you've done. If they're able to link who you are to what you've done, then obviously you have no privacy then. So you have to. So there's tons of applications exploring all of these issues. The key takeaways I want to have though from all of this stuff before, this is pretty much the end of all the more technical stuff that I want to get into, is that users are going to create their private public key pairs to establish identities. They're going to use digital signatures to securely send transactions on the network and to be confident in their integrity. That the network itself is going to maintain this distributed ledger by choosing the blockchain that has the most proof of work that has been done on it. And that the blockchain is updated through this process of mining, which is provably difficult, so that we know that work has gone into creating the blocks. And that once transactions are included into the blockchain, we know that they are recorded permanently and irreversibly. So now I'll go into some of the other applications where blockchain is used. Now, not too much. We're only going to cover a couple quick things here. Ethereum does a lot of things, but in terms of the context of what I've been talking about here, it introduces something called smart contracts. We have quicker block times on the order of 15 seconds instead of 10 minutes. And there's also currently going on this talk about transitioning to proof of stake for consensus, which is going to try to use a consensus mechanism that doesn't use as much energy, essentially. On Ethereum, we have two types of accounts because of this introduction of smart contracts. We have accounts that are controlled by private keys, much like Bitcoin accounts, and we have accounts that are controlled by smart contracts, which can have an owner, but are fundamentally controlled by smart contracts. And this is where you might hear people talking about how code is law, because whatever's written in the smart contract, you send Ethereum into this contract, it will do whatever the code tells it to do. Now, there are some pros and cons to that. And to get into that just a little bit, Ethereum smart contracts are running on something called the Ethereum virtual machine, which is in each Ethereum node. So if you have a full node and you just launch a computer and you download the full Ethereum wallet, you need to download the entire Ethereum blockchain to become a full node, and in doing so, you will actually be processing every smart contract transaction that ever occurred on the network. So I've seen that a lot of people don't realize that at first, and it kind of it's a little bit of a buzzkill, honestly, when you see that. Again, though, many applications that explore that limitation. Ethereum also introduces a Turing-complete scripting language. Now, Bitcoin has a very limited scripting language, and it's very ugly to read and write. Ethereum introduces this thing called Turing completeness, which, if you're not familiar, is basically going to mean, as programmers, we can write code with loops and recursion. Why? Nobody, there's not really many applications that are known for smart contracts, for actually useful smart contracts. There's really only been a few very fringe applications which have been dreamed up of that actually involve the use of loops, or that will necessitate the use of loops. So this introduction of Turing completeness, again, not to be a total buzzkill. I've made my whole living on Ethereum, so I probably shouldn't be trying. But anyway, but you know, it's not exactly, I think, what people thought it was going to mean. What is sort of interesting, though, is that Ethereum smart contracts have access to information that you wouldn't have when you're scripting with Bitcoin. And it has access to information about the blockchain, like what block you're on, and different information that would be in the header. And also it has access to other smart contracts. So you can write these decentralized applications which can interact with each other in various ways and invoke on each other, and so you can create much more complex behavior on Ethereum with smart contracts. And this is typically done. The most popular language that is used to develop these smart contracts right now is called Solidity, which is based on JavaScript. And there's a bunch of languages that are being developed that are inspired by languages that people are used to, but this is the one that by far has the most traction out of them. And so, applications. Here's a viable application of CryptoKitties, which sounds ridiculous, but I will remind you that it raised $12 million in venture funding. And maybe not without good cause. I mean, other than being a cute killer application that nearly brought down the entire network, because so many people are using these, buying and messing with these CryptoKitties, that it ended up being a large percentage of what the Ethereum virtual machine on every node was having to deal with. Aside from that, there is, if you abstract the technology of CryptoKitties, you can create a bunch of different things. You can use the same kind of concept to create things like land registries, and even to use the same kind of coding like here. As you can see, this is a Solidity code. You can use just code like this to create tokens. And you see a ton of tokens that you'll be led to believe are actual blockchain networks, but are actually just things that people have created to raise money for a future blockchain network. And these things are called Ethereum tokens. There's a ton of these that if you're buying them on exchanges, you can look out for. I think it's changed now, but I know EOS was one that was really big. You hear it's this platform that's going to be competing with Ethereum, and then your token for EOS isn't actually on an EOS blockchain. It's actually an Ethereum token. So you have to look out for stuff like that. But regardless, smart contracts do allow us to do things like you would not have been able to build CryptoKitties in the same way on Bitcoin. So Ethereum, there's the smart contracts introduced there. The way that they're abstracted so that more casual coders can actually interact with them and create them. It does have a lot of benefit. It also has drawback, of course, because a lot of people can't write code. And so when they try to write code, they end up creating big problems. And the biggest problem that you would have seen on Ethereum, if you happen to follow back in the day, would have been the DAO hack. There was just some sloppily written code that was very easily exploited that had, I don't remember, I don't even want to think of how many millions of dollars in it. So there's trade-offs, but I think ultimately the idea of smart contracts has been a positive one for the blockchain technology, and is something that if you're trying to get into the development, is something that you should definitely be aware of and try to learn it. A quick note on proof of stake. I mentioned this before, I don't want to go into it too much, but currently Ethereum, the Ethereum community is actively debating on, should we switch to proof of stake? Should we switch to a consensus mechanism that isn't going to be as energy consumptive? And if you'd like to actually catch one of these sorts of things happening right now, this is a very high-profile example of challenges in consensus software development. In fact, it's going to be August 31st is their next call, where they're having a bunch of people come in to debate how this should be done and what it looks like. So I would highly recommend checking that out if you have some interest in actually, if it is history, seeing history as it's being recorded. So I want to finish off here with going beyond public blockchains. Yeah, what's up?
So these smart contracts, does that mean that potentially would eliminate counterparty risk in derivatives? Is that possible that does that?
I would hope so. I would hope it's possible, and I mean that's certainly a potential application.
I mean, are there contracts that do that today?
I'd have to do a little bit of. I know there's projects on that kind of stuff, but I'd have to do a little bit of research to know specifically. But thanks for the question. So just to end off here, going beyond public blockchains a little bit, these are the two giants right here, the R3 consortium and the IBM blockchain. They cover a couple of business use cases, let's say classes of use cases, which there's a lot of potential for. And then we'll talk quickly about the Hyperledger frameworks in Microsoft Azure for people who are actually trying to get into development without having to wrangle with all the platforms all of the tools that have been created by the developers. A lot more user-friendly. So the R3 consortium is a collaboration to reform the data layer across the financial sector. Basically, just to think of the way that you have many, many different banks that need to share information all the time, but they're all maintaining data in their own silos. So one application of blockchain that people seem pretty optimistic about is to basically horizontally merge this data layer so that it's lower cost, easier to maintain, and you don't need to trust. You don't have to so closely guard it. You can open it up and trust that it's not going to be faulty. So this is composed of over 200 companies and regulators. Among them, I just picked some of the biggest names: Bank of America, HSBC, UBS, and Wells Fargo. And the technology that they're using to try to implement this solution is called the Corda platform. So that's sort of the general business use case there. Highly recommend checking it out, especially if you have a similar issue. With IBM's created something called the IBM blockchain, where they're partnering with companies across supply chains in order to kind of go the other direction. So looking horizontally and trying to consolidate the data layer in that way, just looking vertically in like the farm to table kind of sense, and take all the different businesses along the way and find a way for them to share their data so that they can all rely on it and for it to be cheaper. So IBM is very actively trying to build up this platform. And these are just some of the lines of what they believe they can do with it from their website. They can reduce or eliminate fraud and errors, improve inventory management, reduce delays from paperwork, identify issues faster. It sounds great if it'll work. We'll see. If you're interested in actually developing on a blockchain platform, I highly recommend checking out Hyperledger. They're an open source collaborative effort featuring a lot of different frameworks that have been contributed from some major players, such as Fabric here is probably their largest one. It was actually originally contributed by IBM. And it has a modular architecture. You can just plug and play. It's pretty interesting to mess around with if you want to try different consensus mechanisms or even build sort of more private blockchain applications. They have Sawtooth. They have Indie for mobile applications and more. They also have a lot of tools that are going to help with common processes like how you're benchmarking your blockchain, how you're modeling it, how you're deploying it. They have a bunch of things. It's a really, I think it's created by or associated with the Linux Foundation, and they seem to have done a lot of good work in the past couple of years with getting developers, up to speed and running quickly with this stuff. And lastly, I'll talk about the Microsoft Azure Blockchain as a Service. Very similar concept, except instead of having their own platforms, they're trying to help you bootstrap projects that are using R3's Corda, Hyperledger's Fabric, or just Ethereum. And I'm actually personally interested in checking this out because I've done some work on Ethereum and had to deal with that and on all of their tools and all the intricacies there. I'm really interested to personally see how Microsoft has been able to abstract a lot of that away and create a streamlined and more manageable experience when you're developing a blockchain. So yeah, Hyperledger and the Azure Blockchain as a Service are very interesting to me as far as learning how to develop with this stuff. So that's going to be the end for me here. I just want to leave you with a couple of resources. This book, Mastering Bitcoin by Andreas Antonopoulos, a lot of the material from this is from this presentation is derived from this book. It goes into a lot of excruciating detail. If you love the bloody details, this is the book. I didn't talk about history of Bitcoin at all because I'm not at this point very interested in it. We're trying to move forward, but if you want to learn about the history of Bitcoin, highly recommend this book, Digital Gold by Nathaniel Popper. And then I also just keep up with the space using CoinDesk as for the news, and there's just some other almost historical documents at this point. The Bitcoin white paper and the Ethereum white paper contain a lot of good information on why things were made the way that they are. So thank you for coming here. This has been an interesting experience putting together this presentation. I hope you're able to take something from it. Please feel free to attend Lehigh Valley Crypto Tech. It's a meetup that I organize. It meets on the third Thursdays of every month. It's always an interesting crowd. We meet up at the Braveheart Inn in Hellertown, so it's a very, very cool environment. And if you're interested in mining, please get in touch with me. This is our website, rigshare.io. I can also hand you my card, give you my email and phone number from that. So again, thank you everybody for coming.
Any questions? No questions or yes?
Dumb question, I don't know much about crypto tech, but how many miners you're in the Ethereum world, you said?
Yeah.
So how many miners, how big does that have to grow before, kilowatts outweigh the return? I've seen the question before on news for Bitcoin, but I don't know anything about Ethereum yet.
Yeah, I mean, the thing is, as more and more people join the network, it becomes harder and harder to mine. So sort of what you hope for is that as more people are joining the network, that the price is also going up. And so you're hoping that as you're getting a smaller and smaller return, that it's keeping up. Not always true. So at what point does it happen that it's not profitable is when I shut down my business. I mean, so we're not there yet. So it's something that you have to be aware of when you're looking to getting into mining though. Just to look at the current margin essentially and gauge for yourself how much risk you think there is. Any other questions?
Yeah.
Do you have any opinions on Hashgraph?
No, not really. Yeah, it's interesting. I haven't, because it's sort of, that's the project that a lot of people compare with IOTA, right?
Yeah.
Yeah, so it seems interesting. I haven't dived into the technical details enough to have a good opinion. How do you feel about Hashgraph?
Well, it's patented.
Yeah.
So,
yeah.
trying to wrap my head around that and what they're going to do. For everyone else, because if people think it's a good type of chain, right? Then how are other companies going to do it? Are they actually going to license it? Since they patented it.
Yeah, right. Well, since it's patented, yeah. Like I showed at the beginning, like a lot of companies are kind of getting ready for the intellectual property wars here, and that's exactly what Hashgraph is doing. So, yeah, I mean,
So with the fact that you have the problem with the 51% attack and a lot of these sort of smaller cryptocurrencies having trouble getting off the ground, was it more of kind of like a stroke of luck that things like Bitcoin and Ethereum actually took off in the first place and didn't sort of fall prey to that problem when they were small blockchains starting out, when the Genesis block and
Yeah, absolutely. Because you see with a lot of these new networks now, there are people who are trying to leverage attacks against them. But it was just, under the radar when this technology is new.
And so is that one of the, I imagine that's also a primary motivation to change to something like proof of stake, because that maybe alleviates the problem of these smaller cryptos
Yeah,
that
that's-
can't get off the
that's-
ground because
Yeah, it's certainly a justification. There's many, many reasons. It's another good one.
Any other questions? All right, another thanks to Seed for hosting us, for providing the food, and I think there's probably still some more back there if you want to grab that and just talk amongst yourselves. And I guess when they turn the lights out, they probably want us to go home.
They're automatic lights.
Oh, they're automatic lights. Yeah. So they don't want us to go home when the lights out. Just stay as long as you want, and we'll see you next month, hopefully.
If you're around tomorrow morning, you gotta grab a computer and stuff.
You get dirty work assigned.